Hello everyone, welcome to class 10 lecture on buckling analysis. This is the continuation lecture. So far whatever we have discussed on buckling. So far we have covered what is buckling. Buckling is the stability problem, like when the structure loses its equilibrium configuration under the influence of buckling load and changes its configuration from one equilibrium configuration to the other, and then ultimately it fails under the load, not able to support anymore. It is called instability. So the buckling falls under this category of problem where the structure that is being under the influence of load changes one equilibrium configuration. It jumps from one equilibrium to the other equilibrium. We also saw the variations of the buckled form. We also saw the variation of the buckled form in the plate, how the waveform occurs, and also in column. And then I was also speaking to you on the behavior of different cross sections, or the types of cross section, which is open and closed cross sections under the influence of the buckling load. And also we saw the types of buckling, which is the bifurcation buckling and the limit point buckling, and also the linear elastic and non-linear elastic bucklings. And also I mentioned to you the important considerations you should keep it in mind while carrying out the buckling analysis. And finally we move to the worked out problem of a fixed free column where the theoretical buckling load has been calculated. From the theoretical solution, or from the calculation, we know that the critical buckling load is 32.18 for this geometry. And I have also presented you the same problem that is being run using the finite element tool, which is the Patron and Nastran, where the column has been idealized as 4 bar elements which are interconnected at the nodes, and which is fixed at one of the node, and the load is being applied at the other node. From the Nastran output file F06 file, we got the result, the buckling load factor as 32.18, which is exactly the same with that to the whatever we calculated using the theoretical formulas. And if you look at the F06 file, the eigenvalue here refers to the buckling load factor. It is 32.18. It matches to the theoretical solution whatever we have calculated. So now we'll start discussing on the more on the Nastran parameters for the buckling analysis. So, and the steps what we need to do while carrying out the buckling analysis. First of all, the linear elastic buckling analysis is solution 105, which is the Nastran solution. Similarly, we saw in the previous lectures that the linear elastic analysis, simple linear elastic analysis is solution 101, whereas the buckling is the 105. And then the Nastran solver runs the static analysis. Actually, while when you are carrying out the buckling analysis, Patron generates two types of load cases. One is while writing the deck. One is the static load case, where the structure is treated as a simple static problem, and the reaction forces will be computed and the element stresses will be computed. And then there will be a buckling load case also. So the Nastran solver, what it does is first it runs the static analysis for all the static load cases, and it computes the element internal loads, and then the solver automatically picks up the buckling cases and it generates the eigenvalues and eigenvectors. So each buckling case within the Nastran BDF file will have the corresponding eigenvalue and the eigenvector. So what are all the important considerations that we need to keep in mind, or a stress analyst need to keep in mind for the linear buckling analysis. First of all, the linear, when you say linear, the it already represents that the your stresses and the material behaves the Hooke's law, and the stresses are well within the yield point. So stresses are well within the proportional limit, and so the material behaves linearly. So first consideration is the deflection must be small. So when you say small, you can ask me, when you say small, how to quantify this small? Small in the sense, as a engineering thumb rule, or a general thumb rule within the engineering community is, they take the thickness of the component divided by 10, which is T by 10 ratio. Whatever deflection you get should be less than the T by 10 ratio. So that is the general thumb rule we follow. And the second one is the element stresses. The element stresses must be elastic. So it is obviously understood, since it's a linear analysis, the element stresses, the material behavior is elastic, and the distribution of the internal element forces will be remain constant. So there is no major variation within the elemental distribution of the loads. It is what it is expected. And offsets, and another, the point number 4 and point number 5 are the limitations of the tool, which is Patron here and Nastron. So one thing is, while you are carrying out buckling analysis, and if you are having some beam elements or plate elements or any elements that is having, and you have specified offset value in the property cards, you should probably make it 0, or you should remove it. So before you run the job, before you submit the job, or before you create the PDF file, you should make the offset 0. Otherwise Patron gives some errors in the F06 file. It doesn't solve the problem. So that you should keep it in mind. And another limitation within the tool is, suppose you are doing an analysis of the 3D model, where you have used 3D elements, hexa element, tetra element, penta element, like those kind of 3D elements. So what you should do is, you should give some minimum value to the stiffness of the sixth direction, that is a rotational direction, that is moment in the sixth degrees of freedom, that is we call it as K6 rotation, or the drilling degrees of freedom, which is the out of plane rotation for an element. And to that value, to that degrees of freedom, you should try to give some stiffness value, which is minimum value of 100 is recommended. So this command, which is in the Nastron BDF param command, param K6 rod, 100, would solve that problem. So that we have to, that is again the limitation of the tool that we have to watch for. And another thing is, for any structure that is exhibiting the nonlinear material or the large deflection, so what we could do is, like one thing is, you have to run the structure first for the nonlinear analysis, just to understand how the structure behaves. Or suppose you directly run the buckling analysis and you're not seeing the results whatever you are expecting, then it is cleanly understood that you have to run the model first for the nonlinear analysis before you try to attempt to run in the buckling analysis. First run the nonlinear analysis, see how the results vary, what kind of deflections you get, and what kind of things you get, in terms of when I say things, it is the Eulerian, I'm sorry, I repeat. So if you're not actually getting the results what you want from the linear buckling analysis, so it is recommended that you perform the nonlinear buckling analysis first, and then you see the buckling load values, eigenvalues and eigenvectors. Then you uh, ascertain, like how to solve the problem. If the structure is behaving, exhibiting a very large deflections and so on, yes, then the nonlinear buckling analysis would be your close solution to whatever you do the theoretical justification. The linear buckling analysis may not be worthwhile to do it in such a case. So now we'll see the buckling analysis PDF file. So it's exactly the same problem what we saw before, which is the column buckling problem. So as I mentioned earlier that Patron, the Nastran generates two subcases. One is the static subcase and another one is the buckling subcase. You can see that two subcase appear over here. So a method command must also appear in each buckling subcase. Within the buckling subcase, you see there is a command called method. So method here represents the eigenvalue extraction method, which is eigenRL or eigengb method. Usually Langsohn's method is very famous in extracting the eigenvalues. It is one of the methods that Nastran solver uses to solve the problem. And then a static loading condition must be defined and all static subclasses must be placed before the buckling subcase. Yes, and this static subcase is placed before this buckling subcase. So that is automatically placed if you generate the PDF file from the Patron, or if you have to write your own PDF file, then you have to place the static subcase before the buckling, because the solver solves for static before it goes to the buckling. And then correct SPC sets, SPC in the sense it is the single point constraint, which represents the boundary condition, fixed and hinged, those kind of boundary conditions. So all the SPC set numbers should match, and the output requests that apply only to a particular subcase must be placed inside the subcase. So what are all the outputs we are expecting that should be placed within the, here we are expecting the loads from the static subcase, and on the buckling it is obviously the method that drives. When it's a method, it automatically comes over here, eigenRL, this card, it's the Langsohn's method, and we are expecting the where the eigenvalues and eigen vector, sorry. Okay, the little bit in detail to the eigenvalue extraction methods. As we have seen that a method command is required for any buckling subcase, so that it redirects while solving the problem. It uses that particular command, and the we have to specify how many modes we want to extract from the buckling problem and those kind of stuff in this command, and that will be taken into account. So the bulk data entry eigenRL command is used for the Langsohn's method, which is the very popular method, and eigengb method is used for inverse and sine inverse method. So Nastran uses one of the three methods for computing the eigenvalues or for solving the linear buckling analysis. One is the inverse power eigeng and an enhanced inverse power eigengb, and Langsohn's method. So Langsohn's method is computationally very far quick, and then compared to the other two methods. So the eigenvalue format, or the the eigenRL format is the eigenRL, and this is in Nastran command format, and set ID, SID stands for set identification number, and V1 V2 are the upper eigenvalue bounds, and then that means what kind of, you can specify from where it has to start, from what kind of eigenvalue it can start, and what kind of value you need to see. Suppose you know that from the theoretical solution, otherwise you can just leave it blank, and ND is the number of roots that are desired. When I say number of roots, it is the number of buckling modes or number of eigenvalues that you want this software to compute. So now we'll look into the Patron demonstration, and I will talk further more options. I will show you further more options into that, and we'll discuss few other things in the during the demonstration. Thank you.